Council supports both Cocodton Creek and Fountain Rock Parks in Frederick County and works to improve the park experience for visitors. Our membership is open to the public. In addition to the quarterly webinar series, our activities include organizing the annual Master Naturalist program for Fountain Rock, a seed swap, helping with park events, maintaining park grounds, and an annual fall plant sale. Details for these activities can be found at the Nature Council's website, www.naturecouncilfc.org. Next, before I introduce and now for our speaker, we are very pleased to have Randy Bass join us again to present I Am a Naturalist, Not a Meteorologist, Part 2, Climate Patterns and Change, Understanding the Long View. Randy's bio, despite the title, shows that he indeed has a lot of meteorological experience, working across the military, private sector, and federal government. He is a retired weather officer and has supported global operations, the intelligence community, and satellite programs before advancing weather innovation at the Federal Aviation Administration. He is currently the founder of Bass Weather Services, providing forecasting, research, and consultation to businesses and legal teams. And with that, I will turn this over to Randy.
All right, thank you very much. You said, you stole some of my thunder, so I actually saved some time. I won't have to go through my bio again. If you joined us back in, I think it was early December, we talked about weather in general, but this one is going to be more on the climate side. So I'm going to talk a little bit about that. You can see. I will not be talking about pennies from heaven or anything like that, that kind of climate change, but instead we'll talk about actual climate. So again, I've kind of titled this, I'm a naturalist, not a meteorologist. From your perspective, not mine. I am a meteorologist, but I'll try to give this in a fairly simple to understand terms. I'm not going to use any formulas or anything like that. I don't even like those things. So, but again, we're going to concentrate on climate today. Again, just my biography. I do have many years of meteorological experience, but I won't go through the rest of this because you've already done that, and so that'll save us here a couple of minutes. What I will be talking about is we're going to start out with basically, what is climate? Doing a definition of that, different climatic zones, U.S. climate and weather. Then we'll get into Maryland climate and weather. And so that gives you kind of the background of climate. Then we'll talk a little bit about El Nino and La Nina and how they impact our weather from a climate perspective. We're going to briefly talk about the composition of the atmosphere, because once you get into historical climate and climate change effects, you really got to understand how those changes are from I wouldn't say from a chemical standpoint, because we're not going to get that deep, but just to understand kind of what's going on there. And then we'll finish up with those climate change effects and impacts, and that'll be it. Like I said, if you have any questions, feel free to put them in chat. If I don't see them or I don't answer it for some reason after a minute or two, I'm perfectly fine with you just jumping online and turning on your microphone and saying, "Hey, I have a question." So when we talked a couple months ago, we talked about weather, and weather is what you experience right now. It's the local effect. It's what you're seeing now. Climate, on the other hand, is the average of weather conditions for a particular location over a long period of time. That time could be weeks to months to millions of years, and because of that, you have to do it in different ways. So the climate system itself and the changes in time occur via the influence of its own internal dynamics, kind of like I was talking about. El Nino and La Nina are just one of those. Um, External forcings, volcanic eruptions, solar variations, orbital forcing. The tilt of the Earth has not always been at 23 degrees. It's been a little different over the millions of years. Um, that has had an impact on climate. Um, and then there's anthropogenic forcings, including the changes in the composition of the atmosphere, um, you know, even pollution, land use, changes in the environment due to basically human and animals and things like that. Um, Climate's measured in different ways, depending on really how you look at it and the time scale you're looking. If you're looking back, over a period of a millennium or millions of years, we're looking at things like ice cores and rocks and tree rings and things like that. If you're looking at more short term over months or years, now we use weather satellites and other instruments for that kind of uh, uh, tracking. So for modern day determinations, we use an average calculated over a 30-year period. And then that average is redone every 10 years. So right now, the current average is used from 1990 to 2020. And that just kind of gives you a baseline to see, are there any short-term or little longer-term changes in the climate based on that time period that just ended. So the normal high and low temperatures, for example, that your local weather forecaster may talk about. Those come from those 30-year averages, and we'll talk about how those have actually increased later on in this talk. Um, I will say if you hear about any kind of other averages that are less than 30 years, just take like I said, take it with a grain of salt. Just understand that when you're talking, 10 or 15 years, a couple of outliers can really impact that average. And a good example of that is back, geez, 30 years ago now when I did my thesis. I was doing it on lightning climatology. And at that time, the Lightning Network had only been around since the late 80s. So I only had about 10 years of data to work with. And I was specifically looking at the area around a Whiteman Air Force Base in Missouri, which is about 50 or 60 miles north of Kansas City, and somewhere in that area. And when I looked at it, I got this strong signal of a lot of lightning strikes in that particular area, as opposed to the surrounding area, Iowa, the rest of Missouri, Kansas, Nebraska area. And the way it looked was we thought that might have been a signal of an urban effect from Kansas City itself, the urban heat island causing higher temperatures. Winds are normally from the south or southwest in that area, pushing that heat farther north, combining to create thunderstorms in that area. And me and my advisor thought I was really onto something until we took out 1993. In 1993, there was a lot of flooding throughout the Mississippi Valley, and just about thunderstorms every single day. When we took that out, that signal went away and everything averaged out. So again, just when you see something like that, just be aware that it might not be as accurate as it could be if there was a longer period of time that was taken into account. So the uh, the world is kind of broken out into five major climate zones. So we're going to talk about that a little bit. There's the polar zone, which obviously Antarctica, which isn't really shown here, and the very southern tip of South America, and then up in the Arctic regions and far northern parts of Siberia. The cold zone is most of the Northwest Territory of Canada, much of Siberia, and getting into the uh, Norway, Sweden, and those far northern European countries. Moderate zone is most of the, or at least the northern half of the U.S., most of the U.S. probably, and then a large expanse of Europe and Asia, and then you get into the subtropical zone, which is it's typically a lot of desert areas and very warm areas, but the most of the southeast U.S. is included in that as well as the uh, parts of like Arizona and Baja of Mexico areas, and as well as farther south into the southern or the southern parts of South America, uh, Africa, and most of Australia. And then you get the tropical zone, which is right very close to the equator, say 10 or 15 degrees either way. So that's how on a worldwide basis it is. But you can drill down from that. And when you get down to the U.S. itself, you see that we do have different climate zones here. Our area is more of they call a temperate continental climate. You've got the true subtropical climate down to the southeast. But then once you get out west, you've got a what they call a prairie climate, and then the mountain climate itself, and of course we have a desert climate as well. And then Alaska has its own separate climate areas. And so you can see as you break down, but we can go even deeper than that, and we can get into a particular state like Maryland, and Maryland has different climate zones. And as you see here, looking at the map, basically anything from about I-95 south and east is what they call a maritime affected climate zone because it's modified by basically the Chesapeake Bay, in the Atlantic Ocean area. Um, so it's the temperatures are moderated by those bodies of water, and they're subject to coastal storms. They were certainly affected a couple of weeks ago when we had the nor'easter come through. The next region, the little green region, is called upland affected. Um, it has a slightly shorter growing season than um, the southeastern part, just because it's a little bit cooler, but it has a little bit more increased precipitation, especially when it's compared against a little farther west, the valley affected area that is actually drier than most of the rest of the state, because a lot of times these storm systems that come out of the west and towards the east basically rain themselves out over the mountains, and so you actually have a little drier area there over the valley. And the next one is the mountain affected, which is because of the increased elevation, a little cooler temperatures, a little more precipitation. And then the final one is the areas around DC and Baltimore is the urban affected, and like I said, basically the almost urban heat islands, because of the increased heat. Not necessarily, it says given off by human-made objects, which is partially true, but also things like concrete that absorb that heat and then radiate it back into the lower atmosphere to keep us warmer. So. So when we talk about weather in the United States, and from a climate perspective or an average perspective, in an average year, the U.S. experiences about 100,000 thunderstorms, of which about 1 out of every 10 is considered severe thunderstorm, and that's either contains wind gusts of 58 miles per hour or 50 knots, or greater, or hail of 1 inch or greater in diameter, or of course tornadoes. So, like I said, about 1 in 10 of thunderstorms is classified as severe. We experience somewhere between about 20 and 24 million cloud to ground lightning strikes per year in the U.S. Majority of those are Florida, and then the Central Plains, Oklahoma area. Um, uh, I should have looked, but I believe last year for some reason we had a big spike in lightning strikes. I think it was somewhere around 28 to 30 million. That seems to be just an anomaly. Like I said, normally it's between 20 and 24 million. We average about 1,200 tornadoes per year in the U.S. Most are fairly uh, weak EF0 tornadoes, but still we get, any tornado is severe and can cause damage. So we have quite a few here. And typically we have about two landfalling hurricanes per year, although we did not have any in 2025. Hopefully that doesn't mean that we're going to have four in 2026 to make up for it, but the overall average is about two per year. And that's just on kind of the convective side of weather events. We also have winter storms, Arctic cold outbreaks, floods, summer heat, high winds, wildfires, droughts, and other things that we all have to deal with, at least here in the U.S. On average, the our area experiences somewhere between 27 to about 45 thunderstorm days per year, and yeah, and hopefully you're not experiencing any difficulties in the video, but if you are, let me know as well. Um, and you notice that the time period on this one is 25 years, not 30, but I think in this case it's probably pretty close to the what we would expect. Um, but you do see that this little area of increased thunderstorm activity does seem to go over the DC area and almost to Baltimore, but just north of there and in the Frederick County area and that area, you're a little bit less, and we'll talk a little bit about that as well. There we go. So that was from a U.S. perspective. From a Maryland perspective, Frederick County itself averages between about 35 and 40 thunderstorm days per year. Um, the state itself is usually under about three severe thunderstorm watches per year. I actually think that number might be a little bit low. I think it might be a little bit more than that, um, but especially for the northern half of Maryland, that's probably pretty close. Statewide averages about four tornadoes a year. Unfortunately for them, but fortunately for you, most of those tornadoes do seem to occur in the um, southern part of the state and the eastern part. Um, but you do get a rather even amount of precipitation per month. You don't have a true dry month or a true wet month. It averages generally between, say, 2.5 to about 4.5 inches per month, and it's pretty steady within that range. The main weather patterns flow from west to east. So when you get those, you are somewhat protected by the mountains to the west. As far as um, I think that keeps us from getting some of the severe weather, the severe thunderstorms that they get out in the Midwest and the plains. The uh, the mountains actually protect us and block some of that. We do have a secondary weather pattern from the south to the north, from the Gulf of Mexico and the Atlantic Ocean um, towards the north, and typically when we get severe weather, it does typically come from the south or southwest for around here, not counting, of course, tornado or hurricanes and tropical systems. So as far as Maryland temperatures, the mean annual temperature ranges from about 48 degrees in Garrett County which is the far western county, to about 58 degrees Fahrenheit in the lower Chesapeake Bay area. So there's a good 10-degree difference, average difference in temperature, and that's pretty large for a fairly small state like Maryland. But that's the impacts of of being near the coast and also having mountains. Frequently, it's 10 to 15 degrees colder on the Allegheny Plateau than the eastern portions of the state. As far as precipitation, the mountains get much more than some of the other areas. They average about 48 inches, and then the eastern shore also gets about the same amount. But the Cumberland area and that rain shadow that I mentioned a little while ago, they get about 37 inches, and 10 inches of or 11 inches difference in rain per year is very significant when you're only talking less than 100 miles, probably even less than 60 or 70 miles. That's a pretty big difference in the amount of precipitation in a very small uh, range. As far as thunderstorms, again, around 30 per year on the eastern side of the state, 40 on the western side, and you wouldn't think that mountains would get more thunderstorms than the east side, but they actually do because they get those systems that are coming from the west. That upslope of air actually drives their thunderstorm rate higher than it is for the rest of the state. Same thing with snow. You get 8 to 10 inches or so average on the eastern shore. This year, notwithstanding, because they got a lot more than that 2 weeks ago, where you get you know close to 7 feet of snow in Garrett County per year. Frederick County itself averages about 43 inches of precipitation a year, close to 2 feet of snow per year. Your wettest month is typically May at 4.17 inches, and the driest is typically February at a little over 2.5. And so, like I said, that range is actually pretty small for a particular area. Um, the average July high is around 87. The average January low is around 25. Now that doesn't that's the average January low, not the average January uh, temperature for the day. The average temperature, because the highs in the January are low 40s, the average is probably in the low 30s, but the average lows itself are in the mid 20s. We average a rain day, every 3.5 days. So about twice a week, we typically get rain. Of course, we don't get rain twice a week. We usually get rain 4 or 5 days in a row, and then maybe nothing for a week or a week and a half. We actually average, and this is for most of the area, but specifically for Frederick County, about 200 sunny days per year. So many more sunny days than cloudy and rainy days. Again, as already mentioned, a lot of the weather in our area and your area is really dictated by the geography there. Um, in the wintertime, the water's very cold. The land is also usually cold. You typically get less snow near the coast because the water temperatures are a little bit warmer. There's still, you know, 30s, 40s, even 50 degrees. So that typically keeps the coast a little bit warmer than the rest of the state. Um, but the wind direction is really key. If it's coming out of the north, it's going to be cold everywhere. Whereas it's coming from the south, it could be quite a range of temperatures. But the mountains help to hold in that cold air. Even sometimes when we get uh, winds that are coming up from the south, that warmer air is not as dense as the cold air, so it'll actually ride over the cold air, and so we get what we call a cold air damming effect. That it'll stay very cold near the surface or at the surface, then actually be warmer above the surface. And a good example of that is that storm we had back in late January, where it started out as snow, and then a lot of places, especially Washington South, but even up into Maryland, everything changed to sleet because that there was a warm air above the surface that basically melted the snow as it fell, changed it to rain, and then hit that cold air right or near the surface and refroze before it hit the ground and caused the sleet. Um, Another interesting thing, though, is in the this time of year, many times our area and the DC area up through Frederick and other parts of the state will actually be much warmer than the coast because the land typically heats up faster than the water, and so they'll still get that sea breeze, or they'll stay in sometimes in the 40s and 50s, where we can get up in the 60s and 70s. So that's about the one time of year where they're not nearly as warm as us. In the springtime, the water's still cold, but the land starts to warm up. Again, that warming near the coast can be slowed. But later in the spring, you start to see the sea breezes kick in, where the land will heat up and uh, the air will start to rise, and you'll get that cooler air from the ocean coming in, creating that sea breeze. Sometimes we'll get these what we call backdoor fronts, whereas normally the fronts will move from the west to east. Sometimes they'll actually drop from the north down to the south. The other one is um, like today's a good example. You had a stationary front that uh, kind of sat in between about DC and definitely DC to Richmond, but probably DC to maybe Fredericksburg, where in my area here in Waynesboro, just west of Charlottesville, we were 77 degrees. Washington didn't even make it up to 50, or I'm sorry, make it up to 60, because that stationary front just kind of sat there. You guys were cloudy and cool. We were nice and sunny. So you get these kind of situations, especially in the March, April, even May timeframe, where these fronts will set up and they'll just kind of meander. They'll go a little bit north one day, a little bit south one day, and they'll sit there for maybe a week before something finally pushes them out. Fortunately, this one's going to continue going farther north, and you all should warm up either tomorrow or definitely by Saturday. Um, and the other one is the when we do get those kind of big thunderstorm outbreaks in the springtime, typically the areas near the bay and the ocean won't get those thunderstorms because it'll be too cool, and that cold air is uh, uh, will actually help block those severe thunderstorms from occurring. Once we get into summer, the water is warm, and the land is either warm or hot. The bay and the ocean become moisture sources, and so you'll actually see more thunderstorms start to occur in that area. Sometimes, if you look real good, you'll even see an area of thunderstorms will kind of sit either right over the bay, or even move up the bay or down the bay, depending on the wind direction. And then the thunderstorms will also develop along the mountains and those sea breeze fronts. In the fall, as the land starts to cool, the water's still pretty warm. It takes it a while to cool down. So you can still get some moisture from the bay and the ocean. Um, but in those times, typically the areas near the coast are typically warmer than the rest of the state. But when we get those cold fronts, they can be very dramatic. We can get a lot of wind during that time. But then our growing season ends. But so does tornado season usually, and as we start to turn colder. So, speaking of cold, the uh, we actually just got a new frost and freeze climatology recently, and although I looked at it, it didn't change much from the last one. The For Frederick County, typically the first average of a fall freeze is around 23 October, but of course that can change, on any given year. Um, and then the last average of the spring freeze is around the 11th of April. So even though we're starting to warm up, it doesn't mean that we aren't going to have some cold mornings at least still possible for about the next 5 weeks or so. And even then, we can still get freezes as late as early May sometimes, but typically once we get into early April, the we don't see a lot of uh, freeze freezes in the early mornings. So that kind of gives you an idea of what the averages are from a seasonal perspective. But now let's talk a little bit about what causes changes from normal, at least on a seasonal level, and the primary ones. And there's several others. There's a thing called the North Atlantic Oscillation and things like that. But the two of the big ones that affect our weather here in the U.S. is El Nino and La Nina, and you've probably heard of both of these. They're actually a Pacific coast phenomena where the sea surface temperatures in the equatorial regions of the Pacific Ocean, if they're warmer than normal, it's called El Nino. If they're colder than normal, it's called La Nina. And these produce some significant climate and weather anomalies in the short term. And the short term could be a couple of years, or it could be a couple of months. But the stronger the ocean signal, the stronger and more predictable the atmospheric response is. And so this is kind of the area that it affects, right here, right along the equator. And it's a how they measure it is they it's a 3 month running mean of sea surface temperature anomalies that if there are 5 consecutive uh, uh, months of this 3 month running mean that's above half a degree C above normal, then it's classified as an El Nino. If it's half a degree colder than usual during that time span, it's a La Nina. And here's some really good examples. These are sea surface temperatures, and if you look at the little range here, the little light blue is basically around average, and you can see that at this particular time, and this is an older one, but you can see that this red area here. These are temperatures 2, 3, maybe even 4 degrees above normal for sea surface temperatures in this region. This is a very strong El Nino year back in 2015. 3 years later, 2018, actually just a little over 2 years later, we had a very strong La Nina where the temperatures were 2 to 2.5 degrees colder than usual for these sea surface temperatures. And you can see that when you have these very you strong differences in sea surface temperatures, it affects the atmosphere and it affects the circulation of the atmosphere, so that you know, uh, storms could be directed farther north or farther south than usual because of these anomalies, and that's what causes some of our uh, uh, shorter term atmospheric and climatic changes over a period of maybe even a year or two. Um, right now, we are currently in a La Nina phase, and we have been some time now, I guess maybe a year or so. This one, however, has been very weak. And you see here, um, the temperatures are maybe a degree or so below normal. Um, but we are expecting that this is actually going to wash out, and we're going to transition from a La Nina to a neutral. And I didn't talk about neutral. I talked about El Nino or La Nina, but the third option is neither. And we have very average temperatures through this region. And we're expecting that change to happen basically any time in the next month or so. Um, and assuming that that does occur, although I will tell you, they missed this last year. Last year, they also said it was going to go away, and it didn't. But the expectation is that It'll change over to neutral, and then neutral will persist at least through our summer. Um, Looking back at neutral summers over the last couple of decades, um, for the U.S., we frequently get above average temperatures, but precipitation is kind of all over the place and varies, not only in amount but also location. So be interesting to see if that holds out for this year, but probably not uh, a horrible forecast to believe that at least the temperatures are going to be a little above normal for uh, for most of the U.S., at least for the summer. Typically, for El Nino uh, conditions for the U.S. During the winter time, the southern part of the U.S. is typically a little wetter and a little cooler than usual. Doesn't mean that they'll get snow any necessarily, but cooler than normal. Whereas the especially the far north east and even some of the Canadian maritime areas are typically a little bit warmer, as is the uh, Alaska coast and down to through the Canadian west coast, and a little bit wetter on the even in through the Southern California areas. Um, as far as La Nina during that same time frame, typically it's a little drier and a little warmer for the south, and maybe a little bit wetter for the Ohio Valley, and colder for uh, the same area of the western part of Canada and the southern part of Alaska. However, that didn't happen this year. We were under La Nina during this time period. Um, we all know that at least the eastern half of the U.S. Was much colder than usual. And the West Coast and the western half, the Rockies West, was much warmer than usual. So just because we had, um, I don't know exactly what it would rank as, but probably in the top 20 or 30 coldest winters we've had in the last 120 years, the West Coast had, probably one of their top five warmest winters in that same time frame. So again, that's probably a factor of this being such a weak La Nina, but the relationship did not hold out for this year. Uh, as far as the summertime, the we don't see typically a lot of impacts or a lot of differences in um, our weather compared to normal for either the El Nino or La Nina. Maybe a little bit wetter up in the Cascade area and parts of the Rocky Mountains, but not too much. But you can see some of these other effects that occur, especially over uh, Southeast Asia, and even getting into parts of Australia on both sides. As far as what the expected impacts are for at least the next several months, um, the Climate Center put this out just a couple of weeks ago, saying that they believe that at least the southern half of the U.S. is going to be warmer than normal, with much above normal expectations. And this doesn't mean that this area is going to be much above normal as far as temperatures. It just means they are very confident that this area is going to be above normal in temperature. Um, Whereas, just slightly above percent chance that will, at least the southern part of Virginia will be above normal. But most of the rest of it, just about equal chances that temperature is going to be pretty much even or average, and maybe slightly below chance for the far northern tier of Minnesota and that area, the Great Lakes. As far as precipitation, expecting maybe a little bit better chance of above average precipitation for the Great Lakes regions down into the Ohio Valley, and then drier conditions than normal expected through the desert, especially the desert Southwest and parts of New Mexico. So we'll see how that pans out. All right. So that kind of gives you the uh, an idea of what the climate is for our area. Now we're going to start moving into the climate change part of it, but to get there, first you need to understand a little bit about the composition of the atmosphere. And a dry atmosphere, typically nitrogen is about 78% of that. Oxygen is almost 21%. Argon is pretty much the other 1% of that. And then you have all these other ones that, carbon dioxide is, 4/100ths of a percent. And then you get into these basically parts per million and some of them very, very small. Excuse me. But that's for a dry atmosphere. Uh, and of course, we have water vapor present in our atmosphere, and water vapor is actually the largest contributor to percent wise, and it is considered a greenhouse gas. And it is the largest one by far of the greenhouse gases. So while the desert regions, that water vapor contribution is still maybe near zero, for the average atmosphere, like around us, it's typically around 2 to 3%, um, with maybe 4% in some of the tropics. So if you look at say a normal 2% of the atmosphere is water vapor, that nitrogen drops down about 1.5%. Oxygen drops down about 4/10, and argon drops down a little bit. But basically, that 2% is now water vapor instead of these other ones. Um, and that kind of what that water vapor does is it absorbs that incoming radiation from the sun, and takes a little bit more energy to heat up the air. We all know, in a humid day, or let's say a non-humid day like this time of year, we can easily be 45 in the morning and get to 80 in the afternoon when it's nice and dry. But then comes June and the humidity shoots up, and the overnight temperature may be 70, but we only get to 85 to 90 degrees when they jump up, and that's because that water vapor is absorbing a lot of that radiation from the sun. But at night, it doesn't uh, release that energy back out as outgoing radiation. So that's what keeps us warmer at night, especially during those very humid nights in the winter. So so the next part of this is the you know historical climate. So you know back when the dinosaurs ruled the earth, basically 60, 70 million years ago, the climate was actually much warmer than it is now. Carbon dioxide was much more abundant in the atmosphere. And if you look at this graph here, you can see, around 50, uh, between 50 and 60 million years ago, the global surface average temperature um, here was, around 28 degrees Celsius. That's 82 degrees Fahrenheit as the average temperature of the entire Earth. The current average temperature is around 15 degrees C, or 59. So you can see that, the Earth at this point was much hotter than it is today. And then it started to cool down. And it cooled down pretty rapidly over the next, 10 million years or so, or maybe even 20 million years or so. And then it, kind of stabilized for another 20 million years, or, even maybe 30 million years. But then about 5 million years ago, the Earth took another big dip and cooled down from uh, around 18, 19 degrees C down to actually about 13 degrees C. And a lot of this was back during this period, the all the continents were actually together, and so that as they spread apart, that was probably part of the cooling. There was probably differences in the tilt of the Earth. Of course, you could have had things like asteroid impacts or volcanic uh, uh, events that change some of these, especially when you see these really sharp declines and changes. But overall, that CO2 went from about 1,500 to, or maybe even higher, parts per million, way down once we got to our near term period here on Earth. And the other thing is, the back at this point, none of the Earth was really ice covered, but then we got the Antarctic ice sheet starting, and eventually the Arctic ice sheet was created. So if you look back over the last, say, 800,000 years, and this is using ice core data, um, we can look at the changes in carbon dioxide uh, amounts. And you can see that generally over the last, 800,000 years, it varies and it's almost got a good cycle to it, but generally between about 190 and maybe 290 parts per million. And that's been pretty stable. And then the last 100,000 years ago, we had a big drop off, and then maybe the last 10,000 years or so, it's gone back up. It's just natural variation that we went from 190 back to 200 and maybe 80 or so parts per million. Perfectly natural. Um, just the way the Earth functions. But back in 1958, David Keeling um, started taking carbon dioxide measurements at Mauna Loa Observatory in Hawaii, and this is the longest record of direct measurements that we have. There are other places that take measurements and have taken measurements for a while, but this one is very clean because it's been continuous. Because you're out in the middle of the ocean on the Hawaiian Islands, you don't have the effects of a big factory right downwind that was could cause issues. It's fairly high up in the atmosphere, or it's a couple of thousand feet, I believe, above sea level. So it's a very pristine, clean measurement. And you can see that, back when they first started this measurement in 58, it was around 318 parts per million. It doesn't mean that the entire Earth was that. It was, but at that particular point it was. And you can see over the last, 65 years or so that it's been a very gradual but very distinct and very even warm increase in CO2, basically from 315 to now over 400, and it's about 425. Actually, we'll see what it is here in a minute, what the current one is. But it's gone up over 100 parts per million in the last 65 years. And again, if you go back here, um, we were basically going maybe 100 uh, parts per million over 100,000 years, and now we've done it in the last 65. Um, the question is, how do these carbon dioxide changes affect us humans on the ground? And that's a good question. And there's still a lot of questions about that. And we'll talk a little bit about that here in the next few minutes. But um, it doesn't really affect humans. you're still very low uh, amounts of carbon dioxide. You're talking 400, whether it's 320 or 420 parts per million um, in the atmosphere. The human body is not going to notice that. It's not going to affect us, but it is going to affect things. It is going to affect temperature a little bit, and that we'll talk about some of those effects on the planet itself. I will say, whether it's, regardless of what happens, the Earth does not care. The Earth is going to be just fine, whatever the changes may be. Now, living things on the Earth may have some problems, including humans, but the Earth itself is just going to chug right away, and on its merry way, and it doesn't really care, whether it's completely ice covered or completely ice free. It's just going to do its thing. So, um, but so that's over the last 65 years. Here is the what it's done over the last 5 years, and this is by month, and you can see this good um, variation in month to month. It goes up, and then for a period of time, and it goes down, and the black line is just the average, and you can see that the average just continues to go up. Um, and you can also see that, this peak time here for a particular year, that it's only about 9 months later when it reaches that peak and then exceeds it over the next 3 months or so. And then it drops back down. So I do have a question for you. Why is there a semi-annual variation in the amount of CO2? And if you want to just put it in the chat, that's fine. But just, does anybody have any ideas why it does vary um, at that kind of level? Any ideas? All right. Well, I'll tell you anyway. So if you look here, this is 2021. It is a seasonal effect, right? So this is January. It goes up in February, goes up in March, even into April, May, and then it starts to drop during June, July, August timeframe. Um, and it is seasonal, but it is because, and again, this is northern hemisphere. Remember that. Um, Plants use carbon dioxide and convert it. And so when you get into the springtime season, trees, you know, trees get leaves, plants get flowers, and agriculture's, this is your growing season here. So they're pulling that CO2 out of the air. And then once you get into the cooler time frame of October, November, December, things start going up because all that plant life is dying and decaying. And not only is it not absorbing CO2, it's actually giving off more CO2 than that. So that's why you get this semi-annual variation in the readings. So there we go. All right, so we know that CO2 is increasing every year. Now let's look at something else to see what kind of climatic impacts are going on. And Arctic sea ice is another good one to take a look at. And so starting back around 1979, and it was hard to do this before we had satellites, so most of this is satellite based. Um, we could look at how much of the Arctic Ocean was covered by at least 15% of ice every September. And September was selected because that's usually when the uh, minimum of ice is present, because it's melted during the summer. Once you get into, say, mid-September, things starts to get cold again up there because they don't get a whole lot of sunlight um, in that. at that time, and it starts to refreeze. So that was a good measurement to use, and you can see that it was somewhat stable for a little while, but then starting around 1997, the bottom fell out down to about 2012 or so, when sea ice extent went from, let's say, 7.5 million uh, square kilometers down to about 3.5, so well over half. Um, the National Snow and Ice Data Center uh, measures this and says that since 1980, the amount of ice that survives the summer has declined by 13% per decade. So it's just continued to drop. But you notice here, basically in the last 12 years or so, it seems to have stabilized a little bit. And when you go into it a little bit more, and this is actually, they do measure it by month. They just don't take a look in September. So this is the extent over the last 5 years. But we did add the 2012 minimum here, this little dash line, and then the 30-year average is this gray line here at the top. And you can see that sure enough, the last 5 years have been lower than normal, lower than the average, but it hasn't been nearly as, not quite as bad as the that one 2012 year. Um, because of that, because it has actually stabilized, the uh, Snow and Ice Data Center has not seen any significant downward trend in the minimum extents in September in almost 2 decades now, even with this really bad year. So things seem to be stable. Now we just got to figure out why, because all the projections were that ice extent was going to continue to drop, as an indicator that the Earth was warming. So something else is going on here, and we haven't quite figured out why, but it's probably a good thing that it's at least stable. Um, so now it's a question that we got to find an answer for. Here's another way of looking at it. This is the global average surface temperature. Um, and they kind of arbitrarily chose, I think this is around 1938, as average or zero. But they could have done it as far back as 1880 and started it here. But regardless, it shows that, if you take into account that, between about 1900 and 1920, um, it was about 4/10 of a degree C, so almost 1 degree Fahrenheit colder, compared to at least a degree warmer since then. We're talking about at least a degree and a half of it's a degree and a half warmer C, 2.5 degrees Fahrenheit warmer now than it was back in 100 years ago. If you do that by a decade, it's basically about it rises about 1 degree every 70 years. So if you look at it as 0.14 degrees Fahrenheit per decade, probably doesn't seem like that big a deal. But when you know cumulatively add that up, you do see that there's definitely a trend in our overall temperature going up almost a degree. So it has gone up from, I believe, at this time the global temperature was about 58 Fahrenheit. Now it's 59. So again, overall the global temperature has gone up, but it doesn't mean that it's gone up everywhere, or that it's only gone up a degree and a half everywhere. So here again, another 30-year trend. So they did it right. Um, Looking at it this time from 1994 to 2023, this is a change in degrees Fahrenheit per decade. And you see that the Arctic especially has warmed significantly. You're talking almost 3 degrees Fahrenheit over the poles in the Arctic. Uh, Parts of Europe, almost the same thing. Is warm pretty significantly. Even off the coast, or again the Canadian Maritimes and the Northeast has significantly gone up. But then there's other areas, the North Atlantic and Greenland. Certainly down here and uh, off of uh, Peru and Chile, it is actually gotten a little bit cooler. Um, the northern plains temperature has really not changed at all. So you can see that temperature changes vary by region and by location. So it's not a one size fits all by any means, but definitely the land masses overall have certainly increased in temperatures over the last even 30 years. So what does that mean for, the climate change impacts as far as weather itself? So first of all, and this is US only, 9 of the top 10 warmest years on record have occurred since 1998. I believe the only one that is still uh, uh, not from that time period is the Dust Bowl back in the 30s. I think there's one year from there that is still in the top 10. And from what we have learned on that one, um, that warming was probably human induced, mostly because of bad farming uh, techniques in the uh, in the Midwest and the Plains area that caused that area to really dry out, and seems to have caused that. But on a worldwide basis, that was not true. It was just the U.S. for that one. Since 1896, the average winter temperatures have gone up about 3 degrees in the lower 48. I showed you here. This one is kind of worldwide, but that's over 3 decades. When you break it down into seasons, it's a little bit different. The winter has increased more than the other uh, uh, seasons. Spring has gone up around 2 degrees, but summer and fall have only increased about a degree and a half. And again, that's since 1896. You're talking 130 years now. Um, so summer and fall haven't increased. They've only increased about half of what the winter time has. Uh, Precipitation has increased over the U.S. by about almost 2/10 of an inch per decade. Again, doesn't seem like that much per decade, but when you look over 120 years, that's almost 2.5 inches of increased precipitation uh, per year compared to 1900. Again, that's not going to be at every single location. The West has actually gotten a little bit drier in places and it has experienced more drought, whereas the Midwest and the Northeast have actually gotten wetter. So it could be that some of those areas in the Northeast, maybe they're, 3, even 4 inches above where they were, 100 years ago, whereas the West is either probably not changed or maybe even a little bit drier. And certainly, extreme single day precipitation events have gone up a lot in the last 30 or 40 years, where you didn't have these big, you know, 2, 3, 4, 6 inch outbursts of precipitation in just a few hours that we occasionally see now. So based on all that, what are the changes or what are the impacts to other things like agriculture? So these changes in temperature and rainfall and frost-free days are a little bit longer. It all leads to a longer growing season, and farmers are able to plant longer maturing crops, or maybe even doing more crop cycles, maybe getting 2 crops in per year in their land instead of just one. So you get more food produced. So it's actually been a benefit. So you know you can say, hey, good, climate change has increased our food production, and it has, but because of that, um, when you're talking about a longer, hotter growing season, you may need to increase your irrigation, and that affects your water supply. So you know, water is a resource, and in some cases, it's a scarce resource. And you, Colorado River is a good example of that. So if you need more water, that can certainly be an issue. It also affects when if you plant a crop in March and it starts to flower, but you don't have bees and butterflies to pollinate it because they haven't come out yet, now you have a mismatch. And that decreases the pollination, and now you've got to use other means to do that, or your crops don't pollinate. So there's things that when you look at it from a the black and white perspective, it may seem simple, but when you really get down to it, there's a lot of effects and things that you need to take into account um, that you may not realize when you first look at a this kind of issue. Uh, it affects wildlife. Armadillos, which are typically a southern animal, have expanded their range northwards because of the more mild winters. Although they may be regretting that this year. Um, little story. I Back in the mid '90s, I was going to school at Texas A&M, and I went fishing one day, and this lake outside of town, and it was a pretty decent path to get down to the lake, but there was some tall grass on either side, and I was fishing, and all of a sudden I heard this rustling in the grass right beside me, and you know my immediate thought was that a large water moccasin was about to come out of the grass and come at me, and it turned out to be an armadillo. That was the first one I'd ever seen, but he scared the mess out of me. But back then they were pretty much confined to Texas and that area, but now they've been seen in the Blue Ridge Mountains of North Carolina. They've been seen as far north as Illinois and Indiana. So they're definitely moving north, but like I said, they may be regretting it this year because of how cold it was. Um, a more local impact was the Kentucky Mountain Park is brook trout or the native species, and they need a cold, clear stream to live in. But now non-native brown trout have been introduced. They can tolerate the higher temperatures, and they're still competing for the same areas for bedding and things like that, and the brown trout are actually winning. So the brook trout are starting to decline, or they need to be restocked now where they didn't have to in the past. A couple other ones, the you know, because of the warming temperatures, the rate of sea level rise has more than doubled over the past 30 years, from about 2.3 millimeters back in the 90s to basically double that the last 10 years. Again, over a year, probably not a big deal, but when you put that over 10, 20, 50 years, it starts to make a big difference. Over the last 40 years, Maryland has lost over 25,000 acres of forest and 3,500 acres of farmland to tidal marsh because of the increased sea level rise. You get salt water that moves into these areas and basically ruins the land for farming and forestation. Then you get birds that uh, used to not be in the area have started nesting in parts of Maryland, especially along the eastern shore, and then other birds like the Mississippi kite is now expanded their nesting locations to at least 3 Maryland counties. On the other hand, the sea level rise has led to a habitat loss for the black skimmers. So birds are definitely affected by these climate change impacts as well. So um, with that, that I'm happy to take any questions. Feel free to open up your mics and ask me questions. I will uh, send this presentation over so that you can get copies of it. But again, I'm happy to take any questions you might have. All right. Well, oh, I didn't know that I was pink. I don't know why that does that. Huh. All right. Well, you're very welcome for the it.
Okay.
I enjoy doing these kind of presentations and let me see.
Okay.
Let me see if I oh, I didn't. I was thinking. So if you have any questions that you think of, you can always contact me via email at bassweather, BASS weather at gmail.com, and I am happy to answer those and get back to you. And I saw somebody had their hand raised.
Yeah, my name is Pat. I wanted to thank you for your presentation. Um, what I really got out of it, um, I really loved your graphics showing the incremental increases in how some of these things are changing. And, I don't think we usually see them that way. Track it out over these decades. And I just thought that was very effective. And I want to thank you for your talk.
You're very welcome. And yeah, that's kind of the point. From a year to year perspective, it's very hard to see these kind of things because they get hidden in the noise. Um, there's so much variation on a year to year basis. Like you said, this year, look at this past winter. We were it was pretty brutal compared to what we've experienced the last maybe 15 years or so, especially as far as temperatures. But a lot of people that lived in this area back in the 60s and 70s would say, "Hey, this is the kind of winters I grew up with." Um, but we look at it. We normally compare this year to last year because that's about as far as we can remember usually. Um, but again, these kind of things are hidden in the noise until you tease them out, and you know a small change in one year, like you said, not a big deal. But when you start to build those up over 40, 50, 100 years, there's a noticeable difference. Um, Alan said, the question is how much of these changes are human related, and eh, I my personal opinion is yes. I mean, there some of them are. They have to be look at things. How much is related to? Uh, yeah, I think there's a lot of different things that go into it. Fossil fuel burning and things like that gets probably the most publicity, but I think a lot could be said for things like deforestation. Um, has really changed things. When you take something like parts of the Amazon and cut it down, where you had all that moisture built up in there, they've seen a big difference in rainfall patterns in those areas that um, they don't get nearly as much rain as they used to because the ground is different than it was. How to if that's a local effect, does that affect bigger things like um, jet streams or storm tracks and things like that? And I don't think we've done a very good job of determining those kind of things. Um, I was thinking about something the other day. It kind of hit me that remember going to Pittsburgh a few years ago and reading about the how back in the, I think it was the 20s and 30s, they had to use the uh, street lights were on in the afternoon because the pollution was so bad from the smoke from the factories and things that you couldn't see, and it was actually blocking out the sun. Um, and then if it was true there, we know it was probably true in a lot of other cities and areas throughout the U.S. and a lot of Western civilization areas. Um, we cleaned that up. We did a very good job of cleaning up the pollution. But was the pollution actually kind of hiding some of the warming that was maybe going on at that time? That it was kind of blocking out some of that, and once we cleaned it up, that we're now seeing the warmer temperatures. Maybe it was getting warmer back in the 20s and 30s, but we didn't see it because it was being shielded by the pollution in the air. I don't know. It's just something that I kind of thought of the other day. It's like, wait a minute, there's probably a cause and effect on that. But yeah, I do think that we are contributing to it. I don't know how much, and I think there's still some debate of that. And is it just those couple of things, or is there a lot more to it that even we don't understand yet? So.